This is just going to be the rest of these notes on word problems. So example 5, it says, Ashley decided to save a portion of her paycheck each month. When she started saving, she had $100. After 4 months, she had $200, and after 8 months, she had $300. So A says to represent this data as a table and as a graph. So we're going to fill in the table based on what information they gave us. So it says when she started saving, she had $100. So at 0 time, she already had $100. After 4 months, she had $200. And at 8 months, she had $300. So then we're going to make this into a graph. So something about graphs that's really important is that you label the axes. So we're going to label this x-axis, and I didn't really leave a lot of room there, where this x-axis is going to be time in months. So time in months. So we need to go to 8 months. So I can't count by ones. I can't count 1, 2, 3, 4, 5, 6 because I run out of room. So I'm going to go every 2 months. So this is going to be 2 months, 4 months, 6 months, 8 months. Okay. And then on the y-axis, it's amount of savings. So I'm going to do that in a different color. So on this side, this is going to be savings. And it's in dollars, obviously. Okay. And then we need to go up to $300. So I think we can count by, let's see, we got 100, 200, 300, yeah, every $50. So this first one is going to be 50, then 100, then 150, then 200, 250, and then 300. So you don't have to necessarily count like that, but I just think it helps spread it out a little bit. Okay. So now let's plot these points. So at 0 months, she has $100. So that's not a 0, 0. It's already right here. 0, 100. At 4 months, she has $200 right here. And at 8 months, she has $300 right here. So we'll be increasing like this. Pretend that my line is straight and actually goes through the points. There you go. So the rate of change, so our rate of change is the rise over the run, or the change in y divided by change in x. So because we have a graph now, we could count rise over run. We also have a table, so we could do change in y over change in x. It doesn't matter which one you use. They should both give you the same thing. So if I'm using my graph, what I notice is it goes in 1 month from 100 up to 200. So that's an increase of $100. So the rise is 100. The run, it goes over to 4 months, right? This is 4 months, not 2 months, so over 4 months. So $100 over 4 months is an increase of $25 per month. So every month she's increasing her savings by $25. So her rate of change is 25. The next question, what is the initial value and what does that represent? So the initial value, initial means the beginning. So the beginning value was how much she had at 0 time. So right here is 0, 100, or this point right here on the graph, which is your B, your y-intercept. So her initial value was 0, 100. And what does that mean? That is her y-intercept. Or in real life, it's the money she began with. The money she began with. In her savings, obviously. Okay. All right, next question. Write a function model or an equation to describe the savings S in terms of the time T. So normally our equations are in y equals mx plus b, right? But this time they're asking us to use S for savings and T for time. So just know y equals mx plus b is what we're really writing, but instead of S, we're putting in, or instead of y, we're putting in S. And instead of x, we're putting in t for the x right there. So her savings is going to be equal to her rate, which is $25 per month, times time, which is months, plus her beginning amount or initial value, which was 100. So there is an equation to represent her savings. And then the question asks for domain. So this is a little bit tricky because it doesn't really clarify. Do we want the domain of just the situation, or do we want the domain of what it would be? And that's tricky. So it would have to be very clear on which one it wants because they're different. So for just her situation, we know that her domain starts right here at 0 and it goes all the way to 8. We're assuming that she stopped saving, though at 8 months. So that would be for just this situation. So that I put this arrow on the end would be incorrect if we assume she stops at 8 months, because we would say, well, her savings isn't going to go beyond that. In the real world, if she kept saving, then it would keep going, but we just don't really know. So we're going to say she stopped saving at 8 months, just for the sake of making this domain a little bit easier. So we're going to say she stopped saving. So her domain, her time, right? Our domain is X. So our domain is X, which is time, goes from 0 to 8. So her time, the time is greater than or equal to 0 months, but less than or equal to 8 months. And for that same period of time, then it wants her range. So again, her range would be the Y values. So looking over here at the Y's, we would say that her savings started at $100 and it ends up here at $300. We're assuming that she stopped saving. We don't really know, but we're just going to go with that. So we're going to say her savings is going to be greater than or equal to 100, but less than or equal to 300. Okay. All right, let's look at the next example. So, example 6, the population of Webb County, Texas from the year 2000 through 2010 is shown in the graph. So this is the years since 2000. So this here, year 0 is 2000. Year 10 would be 2010. The question says, what is the rate of change for the population in terms of the year? So again, rate of change is the slope, or the change in Y over change in X. Remember, that's also described as rise over run. So looking at our graph, we have two pretty points that we can use. We can use this point and we can use this point. So the rise over the run. So it goes from right here at 193. It looks like 200, but it tells us it's 193 up to 250. So we need to figure out what is that an increase of. So I'm definitely going to use my calculator. So using my calculator, I want to do 250 minus 193 to figure out how much did that increase. So 250 minus 193 is 57. Okay, that should make sense because from 200 to 250 would be 50 plus the 7 to get to 200. So 57 is our rise. So 57 over our run. Our run would be 10 years. So because we went from 0 years right here to 10 years. So 57 divided by 10, hopefully you know, is 5.7, right? 5.7. So this is a situation that's a little bit different. So I probably would use a decimal just to make this fraction a little bit prettier. That's kind of ugly, so I would use 5.7. Okay. What is the initial value and what does it represent? So again, the initial value is the beginning value. Initial is beginning. So right here, our initial value is 193. So what does that mean? That means in year 0, which was in 2000, population was 193. Not 193 people, because look over here, it says in thousands. So it's 193,000. So 193,000 people in Webb County, Texas, wherever Webb County is. Okay. Last, write a linear function to model the population. So to write an equation or a linear function, all we need is the slope, 5.7, and the b, the 193,000. So y equals 5.7x would be our slope, or our rate of change, plus 193. We're going to leave it in hundreds right here. I mean, it's in thousands, but we want to leave it in like this, because if I put 193,000, then my numbers are going to be so big that my graph's not going to be able to read it. So we'll leave it at 193. But no, that means 193,000. D, if this trend were to continue, what would be the population in 2015? So in 2015, that actually goes off my graph, right? My graph only goes to 2012, so I could kind of make a prediction if I kept drawing the line, but it's much easier if I just know what X is going to stand for. So in 2015, that would be 15 years since 2000. So right here, X would be 15. So I'm just going to put a 15 in right here and then simplify. I'm going to use my calculator to do that. So if I use 5.7 times 15, again, because 2015 would be 15 years since 2000 plus 193. So 5.7 maybe times 15, because it's 15 years since 2000 plus 193. Again, remember this answer is going to be in thousands. So 278.5. Okay, and let me erase that actually. 278.5. And if you wanted to know what that was in thousands, you could just multiply that by 1,000 just to make sure. So in thousands, that's 278,500, or half a thousand right there. So 278,500. So that would be the population, okay, in 2015. So our domain, again, we're just going to go with the domain for this graph. We don't know for sure what they're wanting to know, but we're going to go with the domain for just this graph right here. Population, yes, it's going to increase, but it cannot just continue to increase forever and ever and ever. So one could argue, well, this is just going to keep increasing. And yes, it will. But in the real world, population eventually slows down for lots of reasons. For death, because we don't have access to food for millions and millions of people. I mean, we do, but eventually it's going to run out. So we're just going to go with the population for this graph. So, or the domain and range for this graph. So our domain starts here at 0 and it goes to here at year 10. So we're going to just do for just this graph. So our domain, or years, is from greater than or equal to 0, but less than or equal to 10. Again, that's just of the graph. And then the next one, what is the range? So range would be the population. So the population started here at 193,000 and went up to 250,000. Okay. So again, we're just using this graph. So not really an exact number, but we'll go with the graph. So greater than or equal to 193, less than or equal to 250. Again, those numbers are in thousands. Okay. There we go.